Thank you very much, Rich. I'm just going to get this pulled up. It's an honor to be here. It's a great room. I've not spoken to an audience quite this size before, so it's pretty exciting for me. As Rich said, I'm a member of Disney Research Pittsburgh. It's an interaction design research group, but we're placed within the larger Disney research environment. And Disney Research started about 6 years ago now as a forward-looking research group inside of Walt Disney Imagineering. So we work and publish our work within academic contexts and release our papers to our group, mostly HCI, human-computer interaction conferences, and you'll see we do a little bit more than that. But we also have computer graphics, computer vision, robotics, and RFID, all within the Disney Research Group. We're located at Carnegie Mellon University in Pittsburgh, and we've been there for about, like I said, 6 years now. So again, our group focuses mostly on novel displays, sensors, and interaction techniques. But most people ask, when they see the work, why Disney? And I think that the sort of important driving factor behind our work is not the technology, it's the experience. We're trying to make magical experiences. And this is working for a company that's spent years taking that technology and hiding it kind of in the backstage, and it's got a really it's got sort of that drama background. So it might relate fairly well to some of the museum's interaction design as well. Everything that we do requires a story, a Disney story. We're constantly spinning our work into a pitch that reads as a story. So people look at our work and say, okay, it's very technology driven, it's really interesting, but when we're developing in-house, we have to pitch to each other and to Disney proper as a story, which it's a great driver for us. Our group is made up of a diversity of engineers, scientists, and artists. I think it's the really only way to push the work like that you'll see. I have an art and design background, but I work with electrical engineers, mechanical engineers, computer scientists, and it's really interesting. The artists and designers often bring a perspective that the hard scientists they don't see right up front. And I think this is a model that's starting to be accepted outside of research groups, probably in this community as well. You're working directly with artists in art, so it's one of the things when we present this work at more academic and more scientific conferences, it can be a shock to people. So, like I said, the big idea for our group is to make magical experiences. And then to achieve that, our sort of smaller sub-idea is to make everything interactive. And this falls in line with pervasive computing, ubiquitous computing, the Internet of Things, all of those big ideas about the world becoming more interactive. We are looking at it as a means to make magical experiences, but we're right alongside big companies like Google and Microsoft, other software, hardware companies who are driving those same ideas. I've broken the talk up into these little subsections. The first one is making objects listen. It's kind of this group of sensors, and really just one big sensor. And one of the things that you'll notice throughout the work is we cycle between the story and the technology and the application, and often where we start in developing our research isn't, we don't have a clear idea exactly where we're going to end up. And we have this idea of serendipity, where we're going to stumble upon some solution that we didn't expect at the beginning. And it's not that we're looking for that serendipitous moment, but they just happen, and you have to stay open to those. Whoops, here we go. This is Touche. It's a smart sensor for conductive materials. And the technology works as it's a swept frequency capacitive sensor, so it's sensing various frequencies of capacitance. There are lots of capacitive touch sensors around. You have buttons in museum exhibitions that are just single frequency capacitive buttons. This is a little bit more intelligent than that, so we're scanning across around 200 different frequencies, and it creates a capacitive profile for an object or a person or a plant. And then as another object is added, like a human hand, it changes that profile, and we can read something into that. And we use a machine learning algorithm to derive some information from that and break it down into gestures. So this is the sensor in action. It's really convenient. It's a single wire, just plugs into the back of this door handle in this case. This has already gone through a training procedure where we're building in some calibration and training and teaching the classifier what each gesture looks like. Once we developed the technology, the fun part wasn't really building the hardware and testing it and sending it back and going through 8 iterations of the board. It was getting a chance to take this and stick it onto random stuff in the lab, and dunking our hands in waters and playing with little floating things and figuring out where this could be useful for us. And this is Touche as an on-body sensor, so this is sort of a wrist-worn device where you could use the Touche board to turn the volume up on your phone by, making a gesture with some repetition, and teaching the board. This is the gesture for answer my phone. If you have your earpiece in, something like that. It's moving the input away from the mouse, the keyboard, even the Connect and free air sensor, and placing the input device into the environment and into the objects of our environment. So here's just a nice little chart showing some of the different capacitive profiles for each of these objects. A door handle, a little mobile device where you can start using the case of your mobile device as an input device. A person, and a bucket of water. But we stumbled upon, in this case, the most interesting application, which was hooking this up to plants. And it happens to be a very nice Disney story as well. We love talking objects, plants, and candelabras, and if you anthropomorphize inanimate object, that's a win. So we hooked the sensor up to these plants, and we're able to get these really nice interactions. And we developed this project that went to SIGGRAPH. It's a graphics conference last year. And so we coupled this with some nice visualizations done in OpenGL. We did a little Pepper's Ghost routine. So there's a half-silvered piece of acrylic behind the plants, and as you touch the leaves or the stem of the plant, the sensor knows where you're touching, and it's creating these nice sounds and really clean visualizations alongside of it. We worked with a company called Studio NAND to do the visualizations and the sound processing stuff. They're from Berlin, and it was a really successful installation. The snake plant here worked really, really well. You could kind of play music along this, so we've got, you can tell how far out you are on each of these stems and create these really beautiful sounds and patterns. And the other one that was really good was the bamboo. Bamboo has these breaks along the stem, and you could get very precise location of your hand position on the bamboo, because those breaks act like little resistor capacitor circuit almost, so we simulated it as well, just using off-the-shelf hardware. Oh yeah, here's the bamboo. So that's one of our, I guess, really the only big sensing input project that we've had for a while, and it's been around for a couple of years now. But we're still using it. We use it on other projects, and it's been a really successful piece for us. But going into it, we didn't start this one with the story, let's make plants talk. We kind of circled around to it. We started with the let's make everything talk, or let's make everything listen, rather. So this next section describes giving a little bit more, I guess, voice to objects. And we're going to start with traditional touchscreens. This technology is called electrostatic vibration for screens. It's a really boring name. It used to have a much more exciting name, and then we hit some trademark issues, and we kind of pulled back to electrostatic vibration for screens. So there you have it. Basically what we're doing is injecting a high voltage AC signal into a traditional capacitive touchscreen. And what that allows you to do is to create these synthetic frictional forces on the surface of the screen. So as a user slides his or her finger on the screen, it's catching at certain times when we crank up the voltage or change the frequency or the amplitude of that signal, we can create different sensations to that finger. So typically, you've got your finger sliding on this glass screen, has no haptic sensation, and we're trying to bring something more to that. So let's see. We created some demos where you're able to sense textures. One of the drawbacks of this technology is if your finger is static, you feel nothing. It's only the frictional forces. So you have to feel your finger gripping more or gripping less as it moves. So it's kind of, you might say, competitive with like vibration, mechanical vibration in the screen, but it's kind of affords a different type of interaction. We created this mobile device where the case itself is the ground for the high voltage signal, so it's just all embedded in the screen. I say high voltage signal, but it's, you're not getting shocked. It's just it's high voltage, low current, and just creates these kind of fun sensations on your finger. We also added a camera to the back to try to be able to feel textures. So you've got a live video feed. We kind of abstract that video feed, and you can feel this really rough sensations on the screen. And we've done some studies with the blind, and it's still in process, so that work is ongoing. It needs to be abstracted to a point that you wouldn't recognize the image if you transitioned it to some RGB values, but we're getting closer to using it a more useful application for the blind. So the 2D screen-based interaction was interesting. We really enjoyed the project. We pushed it, I think, as far as it can go. And it was time to break free of the screen and to see what we could do with tangible objects. So this is Ravel, which has a better name. But Revel just stands for reverse electrovibration. So at the top, you'll see this is the electrovibration screen at the top, and what we're doing is reversing that action. We're placing the signal on the user's body and grounding through an object with a conductive coating and an insulating layer. So same idea, same technology, but it allows us to augment the environment, add touch to objects that are around us. So we were able to kind of transition from the screen and break out as you're touching and sliding along the screen. You get that sensation. You can pull it up and actually feel it along the objects as well. So here he is feeling certain certain points on the object and getting these different haptic sensations. We coupled this with depth cameras, and we do that a lot. We use 3D cameras to, not as the driving technology behind our work, but as we augment a lot of our work with the Kinect and other 3D depth cameras. They're used a lot. Yeah, one of the nice things about this project, Ravel, is we were also able to find some nice conductive materials off the shelf. This was a painting that was embedded with a conductive coat of paint. So as users actually touched the physical object, they could get these different sensations. And here we weren't driving the signal entirely digitally, or the sensations weren't changing because of a change in that digital signal. It was also a change in the thickness of materials. So where the artist laid up extra coats of the conductive paint, you'd have a stronger signal, you could have a weaker area. So it was a nice blend of the material properties of this copper-based conductive ink paint and our technology. So we took that, and you can see there's kind of this progression, screen to object to human. And so we decided to drive use that same technology to drive a signal which transmits an audio signal. So this is Ishin. This was a project that we showed at Ars Electronica last year. And what's happening is a user is able to record an audio message into the microphone. The microphone is also providing the signal, the high voltage audio signal. And then as the user rubs somebody else's ear, you can hear this hidden message that they've recorded into the microphone. So it's pretty neat, pretty intimate interaction experience. When it was an interesting experience in the lab when for like 2 weeks we were just rubbing each other's ears. So I tried explaining it to my wife, and I think she got it. So yeah, just like I said, it's kind of like Ravel, but we decided to throw that onto the ear. It was decided, and probably rightly so, that throwing that high voltage signal right into somebody's ear by their brain isn't a great idea for a museum installation. So we went with a much more innocuous application where we put a machined anodized aluminum ear onto a pedestal, onto this little resonant box. And then you could listen to the message using that little box there by rubbing that ear. It was kind of our abstraction. So the video looks cool. We never actually released it. That was probably way too much for the whoever to handle. So like I said before, we use these depth cameras quite often, and one of the things that we found was that there's very little haptic feedback that you can get from those. So we decided to try to create what we call free air haptics, and that's a haptic experience in the air, in the open space. So we're doing a lot of these things where we're tracking, we're waving our hands and clicking buttons and doing whatever with our hands, but we don't get any sort of feedback. If I try to click a button, there's no moment when I really know I've clicked that button except for that visual feedback. Then there's something satisfying about pressing down, on the touchpad and getting that click, that sort of haptic click, and coupling that with whatever visual feedback you're getting on screen. So we developed this project. It's called Ariel. It's essentially a vortex gun. It's creating little vortices of air by firing these speakers, 5 speakers all at the same time. It's compressing the air in this chamber and forcing it down this little nozzle. It's a flexible 3D printed nozzle so that we can track users with the depth camera. That's a little time-of-flight depth camera on the device there, and pan and tilt servos so that we can move those vortices around. Here it is. We pumped in party smoke for the visualization. which was super fun to film and to photograph. It was pretty neat. So then we started to develop experiences, and these kind of wrote themselves a little bit. The vortices had a nice sort of low frequency pulse. You had to give the speakers time to compress and decompress the chamber. So a butterfly flapping on your hand, it fit really well with the technology, what was possible, and the sensations that it allowed. Button presses and swipes, like I said, we used it to generate feedback for this mobile device. It's an iPad where you're scrolling through iTunes and getting your click and scroll feedback. And then we did a little bit of a gaming application using Unity. We built a quick little game. You could feel these seagulls moving around you in free space, kind of a more immersive gaming experience. But again, the experience that we didn't know we were looking for or expect, though we had that story, we wanted to create free air haptics, we knew that, but we again stumbled upon an interesting application, and that was augmenting the environment. So we took this device, and if you can imagine this in your living room, and we were originally just thinking it's going to be pointed at the people, but if it's aimed at the curtains, and you're watching a scary movie, and you get this ripple past on the curtains, that's a magical experience. It's scary but magical. And it was something that we really hadn't thought about until we had this thing on in a room. And we're like, oh, the papers are moving across the table, and it just worked. This next project is a little bit more of a straight interaction project, but it's really cool. It's utilizing Pico projectors. This is called Side by Side. This is two Pico projectors that are augmented with infrared LEDs. So there are two infrared LEDs and a white LED instead of the typical RGB channels in a small Pico projector. There was a filter that made it look green, so I say white here, but you'll see they're all green. Basically, we created two information streams. We created a visible light stream, which is showing the actual content that the users see. And then we've got our invisible infrared stream, which the cameras on each of those wands can see. And there we're presenting AR tags, those augmented reality tags. So these two mobile projectors can speak to one another and can convey their position and some other information about the interaction. Here you can see, there's a cute little bunny. It's not a Disney character, which we don't use Disney characters. And so she, I think did he give the flowers already? Yeah, he's a cutie. And there you can see at the bottom the actual live input to the cameras on each of these wands. In the boxing game, each character has control of the boxer, and they can push a little button to punch. It was a fun demo to do. When kids played with these things, they just go like that really fast and start moving them around. So I guess it depends on the user. We did the typical HCI user interaction scenario, built folders, sharing things. So you can imagine these in a more mobile context where your cell phone, your mobile phone has a projector, and you can share content with a user by projecting onto the wall. And it's a feature that might be here. Last one I'll show. We'll skip the last one. So they're doing, this is a collaborative gaming environment where one's holding the nest and the other's holding the mama bird, and they're pushing the baby bird into the nest. Another sort of area of research that we're interested in is in rapid manufacturing, 3D printing, additive manufacturing, all those sort of buzzwords. And we build a lot of devices in-house, and we had this idea of making everything interactive, and there's this maybe an ability to provide interactive objects outside of the typical device manufacturers. So we could put out these objects that people could build themselves, or could be built in parks or whatever, just rapidly fabricated interactive objects. So it was looking more at that front end of the development. So we used an optically clear photopolymer and created a series of projects we call printed optics. And these are fully 3D printed chess pieces with embedded fiber optics. So we printed the light pipes, we printed the shapes around them. We added that infrared reflective tag to throw them onto it's the old Microsoft Surface 1, but homemade, so a touch surface screen with the camera embedded in the stand. And it was pretty fun. So this is a fully 3D printed piece. We can channel light through it. That's an animation overlay with the light sort of bending around the corner there. And the way that we did this was through misusing the materials in the 3D printer. So this optically clear material was a standard off-the-shelf material. That's what we used for the core. And we wrapped that in the cladding around those pipes with support material. The support material is typically washed away and removed from the print. We wrapped it around these pipes and found that it had just a slightly different index of refraction and allowed us to channel light through an enclosed embedded object. The resolution of the printer is, it's really good. It's a high-end 3D printer, but it's not at the point where you're going to be able to, build fiber optics that are going to send data across the ocean or whatever. But we are able to make small objects, little embedded objects, mobile objects, toys, and that type of thing. This is a D-pad that we created, so fully embedded, all printed on the printer. We pause the print, drop in these electronic components, and create essentially super robust buttons. And it utilizes frustrated total internal reflection, so there's an embedded infrared LED for photo transistors, which are receiving the signal from the IR emitter, and then as you put your finger down on top of this clear 3D print, it's reflecting more or less light onto the sensor. Some touchscreens work this way as well. They're edge lit with infrared LEDs, and they've got infrared camera down at the bottom. So we created also a series of lenses. Look like this. We did embedded LEDs, so these are LEDs with lenses where we added a secondary lens, but it was more just a study to see what we could do with the optics of the light. And this is where, going through this process of, pausing the print and dropping these pieces in, building this up. This is sped up. This is not real time. Take a little bit longer. We stumbled upon a really, really elegant and useful solution for us, and that was to create this really polished internal surface. So typically with these 3D printed objects, if we trap them in, you'd see the steps, the contours of the 3D print stuck that you couldn't go in later and polish these because they were completely enclosed objects. And one time I accidentally left the 3D printer running for too long, and we got this extra layer of material drooping down onto the surface. And we found that those lenses were much more smooth, much closer to the hemispherical input geometry. And we found that if we raised the printer up, deposited material from a height, let it drip down onto the surface, we could create a surface polishing. That was, again, a little bit more of an engineering find, but it was one of those things that if you're just continuing to crank and to make mistakes and sort of that idea of failing forward that Nancy mentioned, that's what we do all the time. You just have to be on the lookout for those moments. We were able to create light bulbs, which was completely not a research part of the project, but the nice thing about working where we do is they let us go out and explore and take these ideas and these technologies and enter design competitions and send stuff to arts shows and do these things. And I think it's really important for a research group to keep a nice balance between art, design, and the hard sciences. And it's one of the really great things about working where we do. I'll try to get through this more quickly. I realize I'm running low on time, and I want to leave an opportunity for you guys to ask some questions. We then took this and really retrofitted it to the Disney story. It's like, okay, we've got these really great 3D printed light pipes. Let's make some cute toys. So that's what we did. This is Papillon. It's a project where we're building eyes for toys and really small character eyes. So it's the characters are Beep, Iggy, and Boop, and they each have their own little nice, unique personalities. One of the interesting parts about these eyes was trying to develop pixel arrangements that were appropriate for spherical shapes, and we looked to nature here and found that the Fibonacci pattern works as both a 3D and a 2D packing scheme, and there's direct mapping from a 2D to a 3D packing. I'll show you what I mean. So this is a 2D Fibonacci pattern that's just tessellated using a Voronoi tessellation. And when it's extruded up onto that spherical surface, you keep a similar pixel size, so surface area, cross-sectional surface area is consistent across the entire sphere. So in some cases, some packing schemes, you might have elongation at the hemisphere or fewer or more pixels at those locations, but because we were 3D printing these, we were able to create these nice, unique packing schemes. We went on to turn these into input devices as well, so we were able to augment these 3D prints, and essentially we were printing our own 3D touchscreen. So it's a spherical object that's both an input and an output device. There's a half-silvered piece of acrylic in there, a camera, and a pico projector. Quickly, just want to get through the last project. Again, I'd like to leave a little bit of time for a conversation. This is paper generators, and this project really, just like the last ones, kind of stood on its own. We had a guy come in who has an electrical engineering background and was really fascinated by this phenomenon of electrostatics and what you can do with these really small amounts of charge that build up on the surface of our body when you scuff the feet in the dry winter day. So we're kind of synthesizing this. This is called paper generators. There's no battery involved at all. So the interaction is utilizing just the input energy from the little girl rubbing the Teflon across that aluminized mylar. And it's driving this little e-ink display, turning it on and off. And basically what's happening is we're starting with a piece of Teflon, charging it. You just kind of rub it against your body or the carpet, whatever, that gets the Teflon charged. You then take the Teflon and you can place it between two conductors or a single conductor, and you start to just move those up and down. So this allowed us to create a variety of input experiences. We could do some sliding gestures, we could do some knocking gestures, and there's this really small voltage differential that's created, and it gives you this really low current, but actually fairly high voltage output. And one of the things that this was good for was affecting e-ink displays and also LEDs. Okay, and here's one of the sliding gestures. The project was a parallel story and technology. So we said, okay, we've got this great idea. We can get a little bit of energy out, but we want to make this into interactive paper. How can we make a storybook more interactive without adding a battery? And so this is a series of LEDs. That's just a little rectifier. You know, it's kind of big and clumpy and ugly, but again, it doesn't require any batteries or any microcontrollers, any embedded intelligence. It's just directly translating your body's motion into light really inefficiently. So it's not like, yeah, there are other energy harvesting technologies that would be much better for, you know, putting in your car or whatever. Oops. Sorry, I just bumped the cable there. There it is. And so we also were really interested in doing this, adding this to some mechanical motion. And there's just so little energy. It was not, mechanical motion was not a good candidate. You're seeing the last 3 strokes of like a 50 rubs to get that little flag to go like that. So it was not really the right output, and that's one of the things that you have to find. But LEDs work really well. So this is just an infrared LED on the paper generator side, and when you use that to transmit some information to the computer, you can imagine you can augment your storybook with some digital content, and that's what's shown here. So that's it. Those are the projects. Again, what's great about working at Disney Research Pittsburgh is the opportunity to work with artists and engineers and scientists and apply to academic conferences and be at places like this and meet interesting people in all sorts of fields. We move constantly between story and technology, and again, one of the things I didn't mention is, you know, very often we're seeing technology that may be sort of at home in a certain field and bringing it into to our field or into some sort of different context and turning it on its head a little bit. So that's another one of our approaches. All this work is available on our website at disneyresearch.com, and we are the interaction group. There you'll see the robotics group, and you'll see work from our other labs. We've got Disney Research Boston, Disney Research Zurich, and Disney Research LA. But the work that I showed today is just the interaction design group at Disney Research Pittsburgh. And that's it. We have time for just a couple of questions, I think. Good. Oh, please just, come up to the microphones.
Thank you very much. That was incredible. I have one burning question, which is when you're rubbing the plants, do you have audio sound for us to share?
Yeah, let me...
It'd be great to hear some of that.
Do we have the... Yeah, I usually just talk right over it, because I'm...
It looked like it sounded pretty cool.
Yeah, I think, I hope these... There is audio, and if you go to the website, you can find clips with the audio, but... I could answer maybe another question while... What do the toys do? They're, again, coupled with depth cameras, and one of the toys was watching the users to see if you were dancing. And the more you were dancing, the more that its eyes started to flash and get really excited. That was one of them. One of them was a little alarm clock where you could kind of just swipe between screens. And the last one was an emotional little robot. So it would follow your hand around and get skeptical and then scared and happy and just show these different emotions. It was pretty fun to build those experiences. Great question. Let's see. I think this just has an audio overlay. This is the type of sound that was coming out, but this is a soundtrack for the video. we've got some footage on the website with sound output. And we've more recently done more of like a musical instrument application. In fact, I think if you search, this is called Botanicus interacticus. There was a Yahoo News article on us maybe a month ago, 2 months ago, and you can see the actual snake plant as an instrument. So it's just, yeah, Yahoo News and Botanicus interacticus, and you'll find it, I think. Disney Research Pittsburgh. It's a great question. There's lots of testing to make sure that the plants are happy, and if you touch a plant enough, it's not going to be happy. So when the projects leave our group, we're able to talk about them because they're we publish this work and release them to academic conferences, and but then once it goes into Disney proper, that's kind of, I don't really know what happens to it. It goes into the machine. Yes.
I'm wondering, since so much of what you've shown us is not yet commercializable, how much of what you're doing is done as open source certification or open source in your work?
So I can repeat it. The question was how much of our work is open, is available as open hardware or open software, and honestly, we're fortunate enough to exist in a world where we're able to take advantage of communities that share that type of thing. We share our work just explicitly through the conference publications. The Touche board that you saw, we couldn't release the actual drawings for the board. That wasn't available in the paper, but there was enough information that somebody came out and built an Arduino version of the Touche sensor and open sourced that, and I think the more people that are using that, the better. It's not something that is our goal and our mission, but when stuff like that happens, it's like, it benefits all of us. It's a good question. Great. I guess that's it. Thank you so much, and enjoy the conference.